What I'd like to talk about is one particular idea or concept about producing liquid water in Mars, and that is to get it from seasonal water frost. So there certainly is seasonal water frost on Mars. Bottom left image shows some of it at the Viking 2 lander site. And is it possible for it to warm up fast enough so that it melts before it all is lost by sublimation to the atmosphere? So conceptually, this definitely works. Question is, does it work really quantitatively if one studies or quantifies all the contributions to this energy balance? And the middle picture here, by the way, is CO2 frost, not water frost. Now, a great deal can be understood about water on Mars is just by looking at the phase diagram of H2O and CO2. And so the water content of a Martian atmosphere is such that it saturates at about 200 Kelvin. So the frost point is about 200 Kelvin. And that's 0.1, 0.2 Pascal of water. The triple point pressure of water is 611 Pascal. So it's sort of a factor of, roughly 4,000. And so what that means is if ice gets anywhere near its melting point, then, there's very rapid dispersal of vapor into the environment. And so that's a significant barrier to melting. Ice just disappears fast. So, it's not, and the way to overcome this or to deal with this factor of 4,000 is to just heat it really fast, right? If you can heat it really fast from 200 Kelvin to 273 Kelvin, then we will manage to melt it. Another peculiarity of Mars is that its atmospheric pressure is around the triple point pressure of water. It depends on elevation and season. But at the datum level, I think it's 520 Pascal. At the beginning of spring, the triple point is 611 Pascal. And so, below the triple point, we certainly cannot have liquid water. But if salt is present, it is possible to even get slightly somewhere below the triple point temperature. Now, there certainly is a lot of topography on Mars. Here there is some alcoves with, gully alcoves with recurring slope lineae in these. And so to quantify, the temperature, to calculate temperatures, one needs a sort of a three-dimensional energy balance model, which I have built over time. And so, includes the direct sunlight, of course, subsurface conduction, which is important, sky irradiance, and particular terrain irradiance, right? So the infrared, which is emitted from land within field of view. And others have had, used similar models. This is just a more advanced, far more quantitative model than has been used previously. And here's one of those model results. So this is supposed to be a boulder, or an idealized boulder, which is a half sphere sticking out of the ground at a latitude of 30 degrees south. And this is actually a movie. And the simulation is several Mars years long, but here I'm just showing a few sols. So the sun rises and the sun sets. And here on the south end, the polar end of the boulder, it's actually CO2 ice. So even CO2 ice, not just H2O ice, CO2 ice requires 150 Kelvin or less. H2O ice just requires less than 200 Kelvin. And there's this enormous contrast between this 150 Kelvin region and the surface, the less obstructed surface. And so, the big changes in time as well as in space, in temperature. And so next is another view of the same calculation, which just is a bird's eye view of these model results. So the first panel here is just the maximum annual temperature. It does get very warm, even at 30 south. The second panel is the number of days, continuous days, below the frost point of water. And so that means water will accumulate, right? So it accumulates continuously, day and night, over 700 sols. That doesn't give us the amount that accumulates, but the longer it continuously accumulates, the more it will be. And then the third panel shows, there's even some CO2 ice. And the last panel shows the time difference between the end of water frost accumulation and the first day with above 273 Kelvin. So this time difference needs to be short for this for have any chance for water frost to melt. And indeed, it is short. It can be a few days. So I'm showing a time series. There's a white cross here behind the boulder. I will show here a time series of what the temperature looks like. So the first panel is actually the CO2 mass, which grows as a seasonal shadow, and then the sun emerges again, and then the CO2 ice disappears. And then the last day of CO2 ice is called crocus day. That's what I'm talking about, crocus melting. And it actually delays the heating of the surface because you can't raise the temperature until all the CO2 has disappeared. And then on that crocus date here, on the lower panel shows the temperature where it rises rapidly, from less than 150 Kelvin to over to 260 Kelvin. And so there's this huge over 100 Kelvin in half a day, right? And then on the second day it reaches a melting point. But this is without evaporative cooling. So this is just the surface without the water frost, so to speak. And so evaporative cooling is an important factor. So there is a paper by Andrew Ingersoll in 1970 who quantified this. So the humidity causes buoyancy. Molecular weight of H2 is 18 versus 44 for CO2. And so there is a strong buoyancy force which creates a turbulent convection. And the humidity just goes back in the atmosphere through this turbulent flux, and then in turn causes sublimation cooling or evaporative cooling. To put it more illustratively, it's sublimation cooling. And so I have revisited this literature, and I find for this turbulent flux caused by convection, by buoyancy, which causes the convection. And the prefactor is a bit smaller, and when it really reaches a total pressure of the atmosphere, which is here put to 500 Pascal in this example, then it has to diverge, I argue, because the partial pressure can never be higher than the total pressure of the atmosphere. And so with that quantification of the evaporative cooling, I updated this plot. So the lower panel now has a bright blue line in addition to the dark blue line. And the bright blue line includes evaporative cooling. So now on a second day, it does not get up to melting temperature. And so we cannot melt pure ice, but we can melt, or if there is salt, right? If the frost is on a salty substrate, which has a melting point suppression, then it may well melt, right? So it's fairly easy to get within 10 degrees Celsius of a melting point, but I under reasonable assumption, I do not reach a melting point. Now that was one geometry and one latitude. How does this generalize? Well, it's energetically limited, right? So one can look at the energy input, and if I look at optimal energy input, perihelion, low albedo, equator, 1,000 Pascal pressure, then the red line still doesn't quite reach doesn't quite go up to a melting point. And then the right panel tells us how much frost actually gets lost from morning till noon. And 1 kilogram per square meter is a millimeter thick layer of water. So, and 1 millimeter is reasonable because of Viking land, there are two sites, so a few hundred microns, and then a sort of a random place. So at the particularly shadowed location, one can expect more water frost. So there is just enough water frost to last till noon, but energetically one doesn't quite get up to melting temperature. So conclusions. So there are geometries like a boulder 30 latitude or common situations where lots of water frost will accumulate seasonally. Even CO2 frost will accumulate. And after that CO2 frost is gone again, the temperature rises very rapidly, 100 Kelvin in a quarter of a day, quarter of a sol. But still, because of evaporative cooling, it doesn't quite reach the melting temperature of pure ice, so one needs some salts, but one can get quite close to a melting point. So I think there's actually brines forming, or can be brines forming periodically every year, for a few hours or so. This work has recently seen the light of the day in this publication listed at the bottom.